Swayam Prabha. Digital India. Educated India.
Okay, so welcome back. So we have been discussing about side channels using power consumptions. So we will try to take a little bit of like change subject and talk about another very important class of crypto analysis, which are called as fault based attacks or fault attacks. So in this class of attacks, we try to exploit the fact that if there is a fault while there is a crypto running, how do you see the faulty ciphers and then utilize them to get the key. Okay, so I'll try to give you a very top level understanding of this with some details, but also skipping some things for the sake of time. So this essentially brings me to first of all understand what are fault attacks. So fault attacks essentially, and try to motivate you why we should study fault attacks. So nowadays crypto is everywhere. So it's in neural networks, public key, cloud servers, like symmetric key, automotives, post-quantum crypto. But all of them essentially, are when the moment there is a crypto running in these kind of devices or applications, they need to factor the capability of fault attacks. Okay, and one of the reasons why they need to do is because faults have become more and more common. So I'll give you some examples. If you are interested, you can note them down and later on have a look at that. Okay, so for example, there was one very popular work which are called as row hammers. So in row hammers, you try to kind of exploit the fact that if there are memory chips like DRAMs, for example, and if you access the DRAMs very fast, okay, that if you have studied DRAM chips, that there is something which are called as the refresh cycles in the DRAMs. Okay, so typically for DDR3 chips, right, it is of the order of something like 65 milliseconds. Every 65 milliseconds, the processor essentially ensures that the DDR3 is refreshed so that it remembers its contents. Now these attack techniques, which are called as row hammers, what they try to do is that they try to kind of access the memory chip very fast, and that leads to bit flips, like a 0 being 1 and a 1 being 0. Okay, and these people have shown to even demonstrate over the network by launching JavaScripts and so on, where you just take the JavaScript and run that, and that shows remotely how you can flip bits from 0 to 1 and 1 to 0. So of course you need to control and observe and things like that, but in principle row hammers can work and you can create faults inside the memory. Okay, likewise you can also have more fancy equipments, like if you come to our lab, you can see there are laser stations, there are electromagnetic fault injections through which you can actually inject faults inside embedded devices. Okay, nowadays probably of Google Coral boards, like many other boards which are essentially commercialized by companies, where they try to kind of run neural network inference engines on embedded devices. Okay, so it is of course like a constant requirement that you need to evaluate that if there is an embedded board, whether that embedded board can be subjected to such kind of attack vectors. Of course you can use more, I would say, low cost techniques like clock glitches and voltage glitches. Like when we started to do our work in this direction, our initial experiments were based on simple clock glitches. Okay, like you take the clock and you try to suddenly change the clock into a faster clock, which leads to setup time violations, and these violations are manifested as faults. So the bottom line is that when you have a thing which is complex, right, then a fault is more likely than unlikely. Okay, and therefore it is quite interesting to see what is the security implication of that fault. So let me take you to this again famous paper at Eurocrypt 1997, where Dan Bonnet and their team showed the importance of checking cryptographic protocols for faults. Okay, so again I will be using this RSA example to illustrate. So the idea is that if you remember what we discussed in one of our previous discussions in our class, is that if there is an RSA decryption, you send an input, say S, right, and you want to decrypt it, then internally what you do is S power of D. So D is a secret and you just do s power of d modulo some n. So this d is often stored in the form of like it's stored in a memory, and we discussed that maybe it's an like w bit string. So you stored this in the form of say d0, d1, so on till di and so on, right? So now let us discuss what would happen if you allow the computation to work as it is, like you get s power of d, okay, and you also allow the attacker to say flip one of the bits. So you create a fault in the memory, okay, and you flip one of these bits. So therefore this di now becomes di bar, okay, and you get a faulty output and a correct output. So therefore in this case you will get the correct output, which is m, and if you do this fault then it will become m hat, which is a wrong result, right? So intuitively, what do you think you will do if there is an erroneous computation? What will you do if there is an erroneous computation? You will just rerun, right? You will say that, okay, there was a fault, let me just try once more, and you go ahead with the computation, right? But interestingly, you have actually leaked the key, okay? So let us try to understand why or how does it potentially reduce the uncertainty of the key. So what you can do now is remember that m is nothing but s power of d, right? M is nothing but s power of d modulo n, and m hat is nothing but s power of d prime modulo n. This is quite easy, right? So now if you take the ratio of m hat and m, then you can see, and it's not very difficult to see, that all the other exponents of d in d hat are same, right, except the ith location, right? So what I mean is that if you do this s power of like d, then this is nothing but say 2 to the power of, if I assume there is a t bit length, so 2 to the power of t minus 1 dt minus 1 plus 2 to the power of t minus 2 dt minus 2 plus so on till d0, right? Likewise there is maybe 2 to the power of I di, right? So you have something like this, and m hat is nothing but same except that your ith bit is di complement, right? And then you have got plus d0, okay? So what will happen if you take a ratio of these two contents, like quantities? Then all will get cancelled out except this, except the ith term. So you will have s to the power of 2 to the power of I and di minus di bar. Does it make sense? Does it make sense? Yes? So now you see that if I take this ratio, I can calculate this ratio, call it as R, okay? So I know, like this di can either be 0 or it can be 1, okay? If this di is 0, then you can see that this ratio, like m by m hat or m hat by m will be say s power of 2 to the power of I, okay? Like m hat by m will be s to the power of 2 to the power of I, okay? Or it is the reciprocal, right? Does it make sense? So what I said is that if di is 0, then di bar is 1, right? So then this ratio is s to the power of 2 to the power of I minus 1, right? So this becomes the reciprocal of s to the power of 2 to the power of I, right? Or it is s to the power of 2 to the power of I. Make sense? Yes, no? So therefore now you can verify this because you know s, you know n, so you can check that which of these two is correct, right? And that actually pops out the information of di. You have now identified what is the ith bit of d, right? So this is a very simple mathematics, but it tells us that if you are able to flip the ith bit, then that is equivalent to knowing the ith bit, right? So this is a very simple illustration to understand that faults can be catastrophic for security, Okay, it can have a very serious consequence. You cannot just go ahead and do the computation twice because you have leaked the key in that process. So now we would like to therefore, so this is a exactly that. So here there is simple mathematics to verify that. So now suppose I want to extend these ideas to something like AES, okay, like what we were studying. So you would like to extend this for symmetric key ciphers, and there was a very nice paper again in crypto in 1997 by Beham and Shamir, where they showed how you can develop a differential fault attack on something like DES. So DES was a symmetric key crypto which was used at that time before AES came into the market, right? So now we would like to understand, say, how I would extend a DFA to AES. I would like to do a fault attack of the AES crypto. So here is a quick reminder of what we have studied already in AES 128. You have got a plain text and you do 9 rounds of encryption. You first of all do an add round key. You follow it up with sub byte, shift row, mixed columns, add round key. You do this 9 times. The final round you have got sub byte, shift row, and you don't have a mixed column, and you just give an add round key. Okay, this is what is your AES 128 algorithm. So now I would like to do a differential fault attack on this. So this is a little bit of more elaboration of the AES 128 process. And one thing that maybe you can verify this at your place is that now you have this AES Python code also, so you can verify it yourself. You can make a single bit change in the plain text. Like you see that here is an encryption that is shown over here. This is the corresponding cipher, okay? And I have just made a single change to the plain text, okay? So you can see that the cipher text is completely, seemingly unrelated to the original cipher text, okay? So there is an avalanche. I was telling you about avalanche in yesterday's class. So there is an avalanche, okay? Likewise, if you change a single change in the error, there is a single error in the key, that also leads to an avalanche, completely unrelated cipher, okay? So this is a desirable property of any good cipher. So now we would like to understand what a DFA for AES would mean, okay? So basically the idea is that you have a plain text, you have a fault-free cipher, and in another instance you have a plain text, and when you are getting the cipher, you do a fault injection. So this fault injection can come from various mechanisms. It can come from the row hammer, it can come from the clock glitch experiment, it can come from the voltage glitch, it can come from things like a laser injection or an EM injection and so on. So the idea, the bottom line is that you create a fault, and I will tell you how to create the fault. Okay, and the objective of the fault, if you create arbitrary faults, it will not work. You can probably not get the key. But if you are concerted and if you properly tweak, then maybe you will be able to get the key. So you need to understand what is the sweet spot in terms of a fault attacker, right? And then you take the fault-free cipher and the faulty cipher, and then you want to do an analysis which will give you the key. Okay. That is the objective of this term, which is called as DFA. So DFA in this case means it's called as differential fault attacks. Okay? Fault attacks or fault analysis, basically. Right? So here is a simple injection setup that you can probably set up in your own laboratory also, because it's not really very costly. You have got a target device. So in this case, it's a, it could be a Nexus board, or it could be a Spartan board, or any other board for that matter. And the idea is that when it does its encryption, you have got, what you would like to do is you basically, have a clock, right? You have a clock because this is a sequential circuit. So you would like to clock it once, twice, thrice, fourth, and so on till 10 times to get the eventual cipher text. At a suitable time, you should be able to kind of inject a fast clock. The objective of the fast clock is that this design is supposed to operate at a given frequency. And if you overclock it, then there will be errors. Okay? And now the objective of the error is not only to create a problem in the computation, but also to get the key. Okay? So you basically overclock the system, or you under voltage the system. These are typical mechanisms, and I will show you later that these are even possible in many of the commonly well-known systems. Okay, so we would like to kind of do an experiment here on maybe on a Spartan 3 FPGA, and we would like to kind of multiplex the clock from a slow clock or from a reasonable clock to a fast clock, but the objective of the fast clock is to create violations inside the circuit, faults inside the circuit, errors inside the circuit. Okay. So now how do we do that? So if you remember the AES algorithm, there are two distinct parts. One, the data path, which we just now discussed. There is another part which I didn't elaborate on, which is the key scheduling. Okay, like the algorithm which gives you the second round key from the first round key, the third round key from the second round key, and so on. Okay, even that can be targeted. Okay, and there are like previous results where people have targeted the AES key schedule and recovered the key. But I will not go into that discussion, but rather I will be focusing more on when I target the data path. That's more easy to understand actually. And then the fault models means like, and any fault discussions, right? I mean, starts with a fault model. So fault model means what kind of faults do you like to inject? Okay. So remember in the AES state matrix, if you remember, right? I mean, we had this nice 4x4, like arrangement of bytes. So we will be assuming a very popular fault model in our discussion, which is called as a single byte fault model. That means the fault can be here. The fault also can be in any other byte. Okay, the fault can be maybe like this is the byte that is corrupted, or any of the 16 bytes can get corrupted. Okay, and likewise there could be like multiple bytes where like the faults are in maybe like in more than one bytes. But I will not discuss again multiple bytes, but I will rather focus on single bytes in our today's discussion. Okay. So now let us see how a fault would propagate if the fault happens at the input of the 8th round of AES 128. Okay. So you start with a fault, and the fault is say like corrupting any of the bytes of this state. I'm just without loss of generality, I've just written the 0th byte, but it could be any of the bytes actually. Okay. And then I allow it to propagate. So it allows, because the fault will propagate. And when the fault propagates, because of the S box, this will be transformed into some other value. I don't know what is that value. There is any arbitrary value. And then we have the shift rows, so it will also go into some byte location. If it is in the first row, it remains in that location. And then comes the interesting part. Remember, we have the mixed column matrix, right? 2, 3, 1, 1, 2, 3, 1, 1, and so on, right? I mean, I believe that you remember in the mixed column matrix, we had this, like matrix, right? 2, 3, 1, 1, 2, 3, 1, 1, right? So these elements were GF 2 to the power of 8 elements, right? And that essentially will operate now on this column. Okay? So what I mean is, if there is a fault, then that means let me just focus only on this column that I have encircled. Okay? So in the first column, if I write this as, like the column in the correct case was say x1, x2, x3 and x4. And if I take this column and apply this mixed column matrix, I'm just writing M in this case for brevity, then that would mean that this column will get transformed into this, like 2x1 plus 3x2 plus x3 plus x4, right? Okay. And likewise, you will have, like maybe yeah, so x1 plus 2x2 plus 3x3 plus x4, and then you will have x1 plus x2 plus 2x3 plus 3x4, and likewise you will have 3x1 plus right. So this is what you will get in the correct case, right? And now imagine that there is a fault. So if there is a fault, then what that means is that in this case this is corrupted. So this becomes x1 plus f dash, right? So now because of the fault, this x1 will get converted into x1 plus f dash. Likewise, this x1 will become x1 plus f dash. This will also becomes x1 plus f dash, and this will also become x1 plus f dash. right? Does it make sense so far? Right? So now that means that if I want to calculate the fault at this step, that means at the output of this mixed column layer, what does it indicate? It indicates that this I have to find out the XOR between this red column that I have written and this red plus like this blue column, right? So if I do it, it's not very difficult to verify that you will find that this fault propagates to this entire column. Okay, so you will probably have like faults like if you calculate this the differential at this point, that means the XOR output at this stage, then you will have I can write this down as say 2f dash, because the others will get cancelled out. Okay, so you will have 2f dash, you will have f dash, you will have f dash, and you will have 3f dash. This is the like XOR, or this is the status of the fault at the output of this mixed column there. Okay, so I will just write down this as maybe out here as 2f dash, f dash, f dash, and 3f dash. So that is the status of the fault. Okay, so now this essentially tells us that interestingly like initially this particular column can take 2 to the power of 32 values because these are 4 bytes. Okay, but now can you tell me like what are the possibilities of this column? How many possible values can this entire column take? So this column, right, is made up of 4 bytes, right? So 4 bytes typically will take 2 to the power of 32 possible values, right? But because of this fault, now this column will take much lesser than that.
2 to the power f is 8.
F is 8. So it will take 2 to the power of 8 values. Exactly. So initially, so the question was, right, that how many possible values can this column take because of the fault? And now because of the fault, once you fix f dash, the entire column gets fixed. Right? So it will take you only 2 to the power of 8 values. So there is a reduction in the possible number of values, and that means that there is a reduction in entropy. Okay. So now let's go ahead. Because of this subsequent layers, this will get converted into say F1, F2, F3, F4, and likewise, right, there will be a shift row, and as I said that means that this disturbance will go into every column because of the shift row operation, and then comes the mixed column, and that's boom, like this will propagate to the entire state, right? So you will see that these relationships are there in all the columns, right? And this will propagate and get something different, and finally, right, this is what you will observe. So the output differential you can observe, because what you have done is that in the AES engine, if this is your AES engine, you had the plain text, you got a cipher, and now in the faulty situation, if I write it as AES star, you give the same plain text and you get C star, okay, which is the faulty output. Now if you take the XOR of C and C star, you should be able to observe this. But the interesting thing is that now you want to work behind, and you want to go at this point. And for that you need to kind of like guess certain things. What do you need to guess? Is you need to guess the last round key. Because once you want to go back, the last round key will come in between, okay, and that you need to kind of guess and go to this location. So what I mean is that if I like start with, so this is suppose your correct output, say I call it as x1, so I'm just saying for one specific column, like the usual way you can actually think of this in this manner, that is I have given these numbers like A1, A2, A3, 4, but you can also do it in a row wise manner or maybe in a column wise fashion, and that depends upon how you would like to count. But like suppose I have like noted this is my cipher x1, and this is my faulty output, that is x1 plus a1, because a1 is a fault that you have got in the output computation. So what I'm meaning is that a1 is the differential, okay, this is a1, this is the result of C XORed with C star. So if you get a1 out here, then that means if the correct output was x1, the faulty output is x1 plus a1, right? The faulty output is the XOR of x1 and a1, right? So that is what exactly is written here. This is the correct output and this is the faulty output. And now what I do is I guess this 0th key, K00, okay? and then I apply the inverse S box. So this is nothing but the inverse S box. So you apply the inverse S box, and if you do that, then you essentially have come to this point, because this is the input of the S box. Right? Here you are applying the final S box. So what I am doing is I am just going back to this location, and I am verifying whether this is twice this or not, because I know that this byte is 2 times this byte. Right? So I just verify this by doing it this and also calculating this one. For this I need to make another guess, right? Another guess of another key byte, and then I verify that whether this is equal to 2 times this. Right? Likewise, I can also verify whether this is equal to this and whether this is equal to 3 times this. Make sense? So I form these 3 equations. Okay? And I verify. So how many key guesses do you need to do? As you see, there are K00, K13, K22, and maybe K31. So there are 4 key bytes that you can guess. And 4 key bytes will require how many guesses?
2 power 10.
4 key bytes, how many guesses?
2 power 32.
2 power 32. So you do 2 to the power 32 guesses, right? And you verify that whether the guess that you do satisfy this equation system or not. Because in this equation system, everything is known to you except the keys, right? You don't know the keys. You know x1, you know a1, you know a5, you know all the other parameters. What you just don't know is the key. Okay? So some of them will satisfy and some of them will not satisfy. So this will work as a filter, because it will filter out the wrong keys. Correct? Right? Does it make sense? Anybody with any question till this point? Okay. So it turns out that you will find that the number of keys that will survive is something like 2 to the power of 8 to 2 to the power of 9. Okay. So roughly this will essentially, like reduce the key space to only 2 to the power of 8 values, expected number. Okay. The reason why it will do so is also not very difficult to understand. Okay. See, what is the probability in a random experiment that these 2 bytes will match? So if you have got 2 bytes, like suppose you make a guess of a byte and I make a guess of a byte. Okay. What is the probability that they will be same? 1 upon?
Sir, 1 upon 2 power 16.
2 power of? 2 to the power of 16 or 2 power of 8? So you can guess something, right? That is fixed.
Yes, sir.
So it will be 1 by 2 power of 8. Okay. So this probability is 1 by 2 power of 8. Okay. And what is the probability that this equation will get satisfied? That is also 1 by 2 power of 8. Because these are again 2 bytes. Okay. See, and likewise, right, the probability that this will get satisfied is also 1 by 2 power of 8. Okay. So therefore, the probability that all these 3 equations will get satisfied is 1 by 2 power of 24. 1 by 2 power of 8 multiplied by 1 by 2 power of 8 multiplied by 1 by 2 power of 8. And therefore, the expected number of cases which will survive this is 1 by 2 power of 24 into 2 to the power of 32. Because you have 2 to the power of 32 guesses. And that is equal to 2 to the power of 8. So this is the expected number of keys that will satisfy this equation. You know expectation, right, of a random variable. You multiply the probability with the number of possibilities, right? And that is 2 power of 8. Okay. So therefore, right, you can get, and interestingly, right, if you get 2 shots, then you can uniquely retrieve the key. Like if you get, I told you with one fault, but if you get two faults, then you can uniquely retrieve the key. So this was an old paper that was published where we showed that with a single fault, only 2 to the power of 32 possible candidates are there, because remember that so far we have been recovering only 4 bytes of the key, but in AES 128, how many 4 bytes are there? There are 4 key bytes, because there are totally 16 key bytes, right? So now you have reduced it to 2 power of 8 with one fault, but if there are 4 key bytes, the total key size will be 2 to the power of 32. So now what you have done with a single fault, you have reduced the key size from 2 power of 128 to only 2 to the power of 32 values. Okay. So now let's see whether you can do something better very quickly. I will not go in details. So what you can do, so this is what we have studied so far. You can do a first phase of the attack where only 2 to the power of 32 candidates will survive the 10th round. I mean 2 to the power of 32 candidates of the 10th round key will survive this test. So from 2 to the power of 128, with a single fault, you have reduced it to 2 to the power of 32. Does this make sense so far? So the question is, can you do better? So if you observe that in the previous case, we have been exploiting these equations, right? Equations at this point. But something that we have missed out or we have not so far exploited are also equations at this point. So if you go back, right, to this original diagram that we saw, I was exploiting these relationships, right? But then there are some more gold mines apparently here, which I have not exploited. Because there are also nice relationships in this column. The problem is that if I want to go to this, I have to go not only back through the 10th round, but I have also to go back through the 9th round. Okay? And that becomes very complex. So one day we thought that we'll try to go into this complexity and analyze. And very quickly, right, I mean, the idea is that if you have got 2 to the power of 32 keys which will survive this test, and if you want to go behind here, you still have a filtered with probability of 2 to the power of 1 by 2 to the power of 24, because there are still these 3 equations. So what does it mean? That now if you run these 2 to the power of 32 keys, and if you put them into this test, then how many keys will survive? 2 to the power of 32 multiplied by 1 by 2 power of 24, and that is only 2 to the power of 8. So it's a single fault. Now you have reduced the key size from initially from 2 power of 128 to 2 power of 32, and now till 2 to the power of 8, if you can do that. Okay. So but for that you need to kind of understand a little bit of mathematics, which I probably will not have time to talk about, but just leave you with this thought that like if you go through these equation systems, so these are the equation systems which targets these relationships, you will find out that there are 2 equations which actually does not depend upon some of the 9th round keys. So what we did is we wrote like the 9th round key in terms of the 10th round key. The 10th round key we have already deduced. I want to express the 9th round key in terms of 10th round key. If you do that, you will find out that there are certain interesting things. Okay, for example, what you observe here is that these 2 equations do not depend upon 2 key bytes of the 10th round. Okay, it doesn't depend upon K0 and K1, for instance. And that would mean that I can do a nice divide and conquer strategy where I forget these 2 key bytes and do a kind of reduction of the key space, and then do another key reduction by using the other equations. Okay, so you can do this key reduction in 2 steps, and that will still give you the final 2 to the power of 8 keys, but it will give you a 4 times acceleration because 2 bits are not required. So the bottom line here is, after all these things, is that now you can do the key size and reduce it to 2 to the power of 8, but you can do the attack 4 times faster. So there is an open paper, you can, if you're interested, you can go and read it. So finally, right now we have a tool in our laboratory which we have built, which is called as EXP fault, where if you can define this particular cipher, there is a specific language that we have described, and if you describe the cipher in that language, then you can analyze it and automatically come up with this kind of analysis. So right now, initially we did manual analysis, but the whole point of any scientific evaluation is to eventually come up with some tools which can automatically analyze and come up with some guarantees. And I would like to also make this comment before I stop, is that there is this very nice paper, if you are interested you can again look into it. It's called as Plundered Volt, which was published in 2020, where it shows how a little bit of undervolting can create a lot of trouble. Okay? So they take Intel SGX systems, which are very popular 11th generation processors, which were commercialized by Intel, and they try to play around with what is called as the voltage frequency scaling. Okay? So the idea here is, they basically, try to kind of play around with the voltage frequency scalings. Now processors do have voltage frequency scalings. Why do they have? For performance. Okay? Because you know that if certain components are not required or certain components are required, you can actually do a dynamic scheduling of its voltage and frequency. Okay? But now these attackers showed that you can use certain targets and play around with the voltage frequency scaling, the objective being to ensure that the cycle time is less than the propagation time. Exactly like that rudimentary experiment where we started with playing with the clock line. Okay? And then you basically show faults, and then they showed how with a single fault that we essentially just now described, you can recover the key. Okay, so here is a GitHub implementation by a French group of the attack that I just now mentioned to you. Okay, and they showed that how a single fault can subvert and completely recover the key of an SGX systems, and this kind of one of the primary reasons why Intel ended up removing SGX from the 11th generation processors. So you see that these kind of attack vectors are crucial even when you are deploying your systems, and nowadays, right, if you see a processor, most likely it will be secured against such kind of attack vectors. Okay, so the whole point of doing these attacks is not really to sabotage things, okay, but to understand that where are the possible vulnerabilities, because if you understand the vulnerabilities, then you can be at bay from the real adversaries, right? And therefore, right, it is a very important, I would say, responsibility of this community also to report attacks, what we call as vulnerability disclosures. So if you find out a vulnerability, then you should disclose it to the corresponding party, ask their permission before you publish your works. Okay? So therefore, nowadays in any good conference or any good venue, if you want to publish an attack, before that you have to do something which is called as vulnerability disclosure. Okay, you have to do a responsible vulnerability disclosure. They will probably, if they find the attack interesting, they will probably give you an embargo time, which is typically of 90 days or so, and after this you can publish. Okay, so it's a responsibility, because many of these things are used for critical purposes, and therefore it is important to report the findings. So finally, some quick comments about countering fault attacks. How do you really stop these attacks? Okay, and whose fault it is? So the algorithm designer will tell, okay, it's not my fault, it is the fault of the implementer. The implementer will tell, okay, it's not my fault, it is the problem of, the algorithm designer. So that is a dangerous kind of, thing that can happen. And therefore, there are many countermeasures that people have found out, and, some of them which are very common is what are called as concurrent error detection. So the idea of concurrent error detection is nothing but redundancy. So we basically, do a computation twice. So here is a very simple example. So you do an original computation, you just repeat the computation and you compare. Okay, so before you do a cipher, you do the ciphering twice. If the result match, only then you output. Now here is also a catch. What will you output? Suppose, if you find that there is a match, then you output the cipher, right? But if there is no match, then what will you output? Let's see. You can output? No, I mean there is a cipher, right, and there is a faulty cipher. What will you output? So let me say, there can be two strategies. One is that you mute the output. Okay, you don't output anything. But if you do that, that is also an information disclosure, because you are now telling that there was a fault. Okay, so rather the more commonly accepted strategy in industry is that you output a random output. Okay, so you just output some random cipher with the hope that that cannot be exploited. So you basically randomize. So therefore you see here I have written two things, suppress or randomize. Usually I will go with randomize. Okay, just randomize the output. You cannot. So the idea is that if there is a fault, right, then that fault is not usable actually. But that's okay, at least I did not leak the key. So, but the problem is that even, like such kind of, attacks or such kind of countermeasures have also been targeted. And I will just quickly talk about how they do that. So far, one thing that you have to keep in mind is that when you talk about, so why do you believe that this strategy will work? So when I'm comparing two 128-bit values, right, then I'm banking on the fact that the probability that, so it may happen, so how you can break this system? So the way you can break this system is you can inject two faults, okay, in the actual computation and also in the erroneous computation so they exactly match, okay. But then the designer will say that the probability is very small, because if you have a 120-bit data, then the probability that two 120 bits will match is 1 by 2 to the power of 128, and I can live with that risk. In normal day I live with more risk actually, okay. So I can live with that risk. But the point is, this is true when you have a uniform fault distribution, okay. That means all faults are equally likely, then it is 1 by 2 power of 128. So therefore this kind of strategies actually, which are called as classical fault tolerance techniques, works nicely in nature, because nature is largely unbiased, okay. But attackers are not, okay. So the attackers will always try to take your system to a region where it fails. They are biased in their distribution, okay. And if that happens, then calamity can happen. So what I mean is this, that is, suppose you have got, say, these three distributions. In the first case you have an equal fault distribution, okay. So you can see that the variance is 0. But in another case you have another distribution which is more biased towards certain faults. So you can see that here these faults occurred with a larger probability compared to maybe some other faults, okay. So this is more skewed. So in this case you can see that the variance has increased, okay. So likewise this is a more skewed distribution, the variance has increased even further. So now I leave it to you as an exercise to do this check, that is, if there is a variance V which is not 0 of a distribution, what is the probability that there will be a match? So that you can prove is equal to n into V plus 1 by n. So you can see that if V is equal to 0, then this is equal to 1 by n. But if V is not 0, then this can be larger, okay. And I leave it to you as an exercise to prove this. So this means that you can actually, create biased fault models and you can try to exploit. And you can try to fail these systems, okay. So there are techniques in literature where people have shown how to exploit these faults, and in particular this brings us to an idea which is called as differential fault intensity attacks, and basically it banks on the fact that faults are not really unbiased. Are not really, there is a bias in the fault injection. So those of you, right, who understands digital circuit will know that, combinatorial designs, right, like if there is a combinational circuit and sequential circuits, okay. So if I have got an S box, like what we were seeing in the context of AES, right, what is an S box as a circuit? It is basically a lookup, right, which basically takes 8 bits and gives you an 8-bit output. So consider a small example, maybe a 4-bit S box, small example. Often this is very popular in the present day lightweight ciphers and other things. So in that case, right, you have a combinatorial logic where there are 4 input bits and 4 output bits, okay. Each of them are different Boolean circuits. So if you observe the delay in every output bit, they are different because there are different number of gates which will essentially dictate their output. So therefore, right, here is a kind of graph which shows you the delays of all the 4 output bits in the construction, and they are not same, right. So now if you look at the voltage, the clock glitching experiment, what are you doing? You are clocking at that point and suddenly you are bringing the clock down maybe to this point. If you are doing this, then which bit will fail out of these 4 bits? Can all of you see that only the output bit 3 will fail in that case, right? So is this phenomena random? It's not random, right? Every time you repeat this experiment, always output bit 3 will fail, right? So therefore, right, if you are injecting fault by a clock glitch, you can't expect a random phenomena. Every time output bit 3 will fail. So I can control the fault, right? and hence I can create a situation where a countermeasure will fail, because every time I do this experiment, it will be the same fault that will get manifested, right? So this essentially brought to this nice paper from this group in Virginia Tech, where they showed how you can defeat this system by a method which was called as differential fault intensity attack. So very quickly it means that if there is, say, a target location of the fault, and if you inject a fault, then, and if you control the intensity of the fault, controlling the intensity of the fault means that I will clock, but I will always clock at this point. Okay, if I want to increase the intensity, I will bring the fault at the clock line here. That will create more faults. Okay, so this way I have a control on the intensity of the fault. So if I control the intensity of the fault, I know only 1 bit flips, not more than that. Okay, so now with that assumption, what I will do is I will guess this key, okay, and I will basically do a reverse of the S box, and I will find out the Hamming distances. So whenever the Hamming distances are low, most likely my guess was correct. But if I find out that my Hamming distances are large, then that is because of an erroneous guess. Okay, and that is the simple way you can probably distinguish the correct keys from the wrong keys. So that's it. So more or less, I think I'm done. I'll just stop with one few line of research that we are doing at this point. So we are trying to develop a methodology through which we can understand that whether there are faults or not in a black box manner. Okay. So what we are doing is we are taking an encryption algorithm and subjecting it to different kinds of fault simulations, creating faulty ciphertexts. Okay, and then we are creating data sets which has got labels depending upon from which faulty ciphertext label the data is acquired. So that means, what I mean is, imagine suppose you have got this AES state, right, and you are injecting fault here. I inject a fault F0, and in another case I inject a fault F1. Okay, so with the F0 fault I have got some faulty ciphertext data. With the fault F1 I have got another faulty ciphertext data. Okay, and now I am feeding it to a machine learning tool, and I am asking it the machine learning, which is the deep learning network, and asking it to see that whether it can be trained to distinguish between these fault patterns. The idea being is that if it is able to distinguish, then there is a potential leakage. Okay, so we are trying to develop a black box framework where even without going into all the details, you can apply this capability of deep learning to distinguish whether there are potential faulty patterns. So let me stop here with this conclusion that faults can be catastrophic for cipher implementation. We discussed largely a technique which is called as differential fault analysis. I tried to give you some intuition behind bias faults and how they can break countermeasures. And this is a very exciting line of research. We are still working in many other directions in this context. What we look forward is to ideas where eventually, right, we can come up with crypto systems which are resistant against such kind of fault attacks. And so that our present day systems which are running now, and maybe our future crypto systems, maybe post quantum crypto and so on, they should be defiant, because even we have seen based on the research from other contemporary groups is that, and also based on some of our own works, is that post quantum crypto algorithms are extremely vulnerable to faults. Okay, and therefore it is extremely important, given the I would say the stake that is over there, to make them resistant against this class of side channel attacks. So I think I will stop here, and there are, just for a quick reference, this is the book that I largely was following, and there are some other books also which you are interested. By the way, this is a free course that you can download from YouTube. You can also, I think there is a course which is running right now. You can also, if you are interested in hardware security, you can go through this. Yeah, so thank you for your attention. So by the way, ESP Research is an, a startup that we have an incubation out of our lab. So if there is any question, comment, you can of course send me an email to my, usually I like emails which comes to my Gmail, okay, because my CAC email is always at the, I have to always delete mails. So I sometimes delete mails without seeing what is there actually. So I would ask, if you want to send me email, send me to my Gmail. Okay. So I think we'll follow it up with a quick, exercise that Siddhartha will show you about on fault attacks. but so far as the theory is concerned, we are done for our this class. Okay. So any questions? Yeah.
With the fault we want to induce in the 8th round, how do we do that? Like, how do we ensure that it only comes at the 8th round?
So very good question. The question was, how do you control the timing of the fault actually? Okay. So see, I mean, any attack, right, doesn't work alone. So it is always a combination. So I was talking about side channel attacks, right? Remember that I showed you how that 8th round looks like. So if you observe the power side channels, then from there you can get a fair understanding about when the 8th round starts. And that way you can gradually control the site of your fault.
So like the 7 peaks after the...
Yeah. But for your initial experimentations, you can also use a trigger from the circuit. That means the circuit, right, can bring out a trigger, and that way you can control the fault more precisely. But for real life attack, of course, you need to do it without the trigger, and therein you can use the side channel attack vector. Like in one of our recent works, and it is not yet published, but we have reported it to ARMS OPTE, and we have shown like how using a fault injection we can break their trust zone. Okay, so the idea there is that there is a verification check. That means there is a digital signature verification that is being done. We showed a fault injection to bypass that verification check. Okay, and then you can basically offload anything that you want. Okay, so the way we control that is by using a side channel vector. So we saw the side channel, and from there we understood when to time that, and that was used in the injection procedure. Okay, but it is important to control the fault, of course. Any more questions? Okay, so if not, then thank you for your attention.